Hi, how are you? Thank you for showing up here. I'm here to talk to you about two products we've developed that induce localized hypothermia to provide neuroprotection against spinal and cerebral ischemic injury. Our background is we were spun out of Yale University, and through 3 NSF grants and a collaboration with a public medical device company, we've developed 2 catheters, an intrathecal cooling catheter for the spine and a ventricular cooling catheter for the brain. What we do uniquely is we cool the cerebral spinal fluid, which in turn reduces the temperature of the adjacent tissues and organs to levels known to be neuroprotective. The significant clinical benefit is that we're cooling locally into the targeted areas that are injured, and we're maintaining systemic normothermia. And this benefit will hopefully reduce the complications that systemic hypothermia causes, such as shivering, chronic shivering, tachycardia, and the other aspects that have challenged the adoption of systemic hypothermia. We have 2 issued IP, and we have 3 others in the pipeline. Taking a note from Antoine's point last night, one of his presentations, we'll talk about our team. I started way back, I think, after Manny, and probably not as successful as Manny, but I'm trying hard. And I started with Procter & Gamble in their surgical drape and gown division. I then went on to grad school and then went to Becton Dickinson for many years in diabetes care, and both here in Europe and in the United States. Then went to an early stage startup in J&J, and then have done 2 startups, one being Dexcom, the implantable glucose sensor, which I was in Series A and B, and a small company called Medical Instill, in which we sold to Glaxo. My partner from Yale, John Eleftheriades, is the former chief of cardiac thoracic surgery and a world thought leader in cardiac surgery. He's also probably has the most clinical experience in deep hypothermic arrest using hypothermia for aortic arch surgery. So he's a real, he knows quite a lot about hypothermia. My other partner is Dr. Rohit Khanna. He's down in Florida, in Daytona Beach, and he's a significant serial inventor and a big help on helping us move this project forward. Neuroprotection is a significant unmet need. If you think about it, you wonder why hasn't there been more success in neuroprotection? TPA seems to be about it. Well, not much is done because, as you know, the brain is complex and so is the spine. Our first target is aortic aneurysm repair for spinal surgery, which in the thoracic area has a paraplegia rate of 10 to 12% in open repair and 4 to 6 in endovascular. It's still significant, and it's one of the most devastating complications not only that a patient can have, but also the surgical team and the hospital. It's a nightmare. I think most of you understand the brain injury area probably, stroke, TBI, subarachnoid hemorrhage. And what we do is we place the well, I'll get into that in a second. And then the last opportunity is spinal trauma for spinal cord injury. I mentioned this a little bit. It's devastating to the patient. It's devastating to the physician, and the costs to societies to these cerebral and spinal cord injuries are significant. Neuroprotection in the United States alone represents a 250,000 procedure volume a year, so you could double that for worldwide, representing over $1 billion opportunity. These are our products. We've developed them in prototype and used them in 24 animal studies. The top is the brain cooling catheter, and it's very simple. We have 3 lumens in the catheter through which cold saline is circulated in a closed loop. This reduces the temperature of the CSF to neuroprotective levels. The 3rd lumen acts as a ventricular or spinal drain. So this means, which if you think about it, a spinal drain or a cerebral drain is used in every procedure when you're talking about spine injury or neuro or brain injury. So it's a common practice. They're placed, for an example, in brain at the bedside table. So our products have the opportunity to provide additional protective modalities to a doctor without an incremental procedure, because they would be putting in the drainage catheters anyway. So the top is the brain. It goes into the lateral ventricle. The bottom is the intrathecal, which goes just like an epidural in obstetrics. And then we have a pump and controller, which controls the flow rate and the monitoring of the temperature. So how do I know this will be exciting? So my partner took this to the Society of Thoracic Surgeons and showed it in a mock Shark Tank. And the 5 thought leaders who were running the Shark Tank gave it the highest rating. And equally as important, of the 500 attending thoracic surgeons, 73% gave it a thumbs up, and they all wanted to go in. Just like Yossi said the other day in the previous presentation, it was a wow, wow, wow. So I think the clinical need is recognized by the clinicians. They don't have the tools to provide neuroprotection. This is an old school, perhaps, type of product, but it's addressing a significant unmet need. As I said, we're placed in a normal way. The intrathecal catheter is placed like an obstetrics catheter in the spinal cord area, and the brain catheter is placed through a burr hole into the lateral ventricle. This is some of our data from, and I'll show you a little bit more, from our animal trials. On the left, you see our spinal cooling catheter performing, and this is one of our early experiments, where we were able to drop the temperature of the targeted area of the spine down to as low as 29 degrees C. If you think about it, there's a flow dynamics here. We have a circulating fluid, and we can kind of tweak the process by increasing the flow rate and drop temperatures even lower. The top line represents the normothermia. Basically, during these procedures, normothermia was maintained. The one on the right is our brain cooling catheter. These are 5 sheep. Again, we were able to drop the temperature very rapidly to the targeted tissues around the lateral ventricle and then bring it back fairly rapidly to normal levels. So we've done 26 sheep studies for both spine and for brain. In all of them, we achieved efficacy in our ability to cool the temperatures down to the neuroprotective levels. And we did survival studies with the animals to 30 days in some cases, and then 48 hours in the other, to demonstrate that there was no neurological damage caused by the procedure. This is our brain cooling. And when we first did this, I had the assumption, you can see the whole areas of the brain. That's a thermal map, and seeing how we're reaching levels of significant cooling. When we first did this, I thought perhaps we would only be cooling certain areas of the brain, targeted areas of the brain. But when we did the mapping, we showed that we were able to get virtually all of the brain by the placement of one catheter on one side of the brain. So it was beyond our expectations. So we're looking to raise $2.5 million. We've had 3 sub-Q meetings with FDA, and what we will be doing is a last GMP study, and then taking that data and giving it to, putting it in an IDE for a first in-patient study, a 10-patient safety study. So thank you very much.